this is GATE 2017 question number 28, which states that a uniform volume charge density is placed inside a conductor with resistivity 10 to the power minus 2 ohm meter. This is given. The charge density becomes 1 by 2.718 of its original value after time how many femtoseconds? Femtoseconds means 10 to the power minus 15 seconds. So up to 2 decimal places we have to write, and given that it's a free medium, that is free space, epsilon naught is 8.854 into 10 to the power minus 12 F by m. So this is the thing which is given. Now resistivity is given, that means it will tell us about the conductivity, and 1 by 2.718 is nothing but 1 by e, because e to the power 1 exponential to the power 1 is nothing but 2.718. So we will see that what is the solution to this particular question. Okay, so it is given that resistivity of the conductor is 10 to the power minus 2 ohm meter. Therefore conductivity sigma is just reciprocal of the resistivity, that is 10 to the power 2 ohm meter inverse or Siemens. Now to find if volume charge density reduces to 1 upon 2.718 of its original, then how much time have elapsed? This is what we need to find. Now for this we use the conservation of charge, which states that del dot Jf is equal to minus delta rho f by delta t. Just no need to write this f, it doesn't matter, you don't need to write this one because it will confuse. So let me write it first. So del dot J delta rho by delta T. Now rho is the charge density and particularly the volumetric charge density, and so this J is the conduction current density. So J can be written as sigma E, fine, and del dot J is nothing but del dot sigma E, therefore, and delta rho by delta T, delta rho by delta T is del dot sigma E. Delta rho by delta T is minus sigma del dot E, and this is how we can proceed. So again, if we repeat, so del dot J is equal to minus delta rho delta T. So this is the continuity equation where J is the conduction current density, and the conduction current density is given by J is equal to sigma times E, conductivity times the electric field. Now again, if we write the left hand side of this continuity equation, del dot J will be equal to del dot sigma E, and that should be equal to minus delta rho delta T. Therefore minus delta rho delta T will be nothing but del dot sigma E. Taking the minus side in the right hand side, we get delta rho delta T is this. Now what is del dot E? According to the Gauss law, this is rho by epsilon naught, where rho is the volumetric charge density, and delta rho delta T therefore is becoming minus sigma rho by epsilon naught. Therefore d rho by rho can be written as minus sigma by epsilon naught into dt. Integrating this particular equation, we will get this kind of an expression of exponential, that is rho of t, charge density at time t is equal to charge density at t is equal to 0 e to the power minus sigma by epsilon naught t. We can also write this rho t as rho of 0 e to the power minus t by tau, where tau is some kind of a relaxation time. Now this tau will be equal to not sigma by epsilon naught but sigma by epsilon naught inverse, fine, where epsilon naught is given in the question to be this. Now therefore 1 by tau is nothing but sigma by epsilon naught, just this one. So it's 1 by tau is sigma by epsilon naught. So sigma is 10 to the power 2 and epsilon naught is given. So we get 1 by tau as 8.854 into 10 to the power minus 14. So tau becomes 8.854 into 10 to the power minus 14 second. Now e to the power 1 is 2.718, and it is given in the question that rho will tend to rho naught upon 2.718, that is rho naught upon e to the power 1, that is e. Now rho naught is nothing but rho at t is equal to 0, fine. Therefore rho is equal to rho naught e to the power minus t by tau. This expression we have already found out here. Now rho becomes rho naught by e, so just replace rho naught by e. So at what time, how much time, after how much time this rho, this density becomes equal to rho naught by e. So this rho naught cancels, this becomes e to the power minus 1, this is e to the power minus t by tau. So 1 is equal to T by tau if we compare this equation, or T is equal to tau, the time, that is the relaxation time. Relaxation time is the time at which the volumetric charge density reduces to 1 by E times of its original density at T is equal to 0. Therefore, this becomes nothing but 8.854 into 10 to the power minus 14 second, or 88.54 into 10 to the power minus 15 second. Why am I converting? Because the answer requires in femtosecond. Therefore, 10 to the power minus 15 second is 1 femtosecond. 88.54 femtosecond, and up to 2 decimal places this has to be given. Therefore, 88.54 is the actual answer. So what we have done here, we have used the continuity equation, that is del dot J is equal to minus delta rho delta T, which connects the conduction current density with the volumetric charge density. With that, we have proceed where conduction current density is sigma times E. We use the continuity equation and to find out the relation of how the charge density decreases with time. We have got this as the expression, where tau we have found out is sigma by epsilon naught inverse. So tau becomes equal to 8.854 into 10 to the power minus 14 second. Now it is given in the question that if the charge density reduces to 1 by E of the actual charge density, original charge density, then what will be the time elapsed? So that is what we are trying to find out, that using that same expression which we have got, that is rho is equal to rho at T is equal to 0, which is rho naught E to the power minus T by tau. So rho becomes rho naught by E, because 1 by E times the original charge density is given in the question. So rho naught cancels, and we compare and we get that T is nothing but the relaxation time tau, and which is we have already calculated, and we have found out in terms of femtosecond, it comes out to be 88.54. So the answer is 88.54 seconds, femtoseconds. So 88.54 femtoseconds are required for the charge density to reduce to its 1 by Eth value of the original one. So that is the answer. Thank you.